Hello students, welcome back to the classroom point. In our today's class, we shall discuss the hydrogen bond and its consequences along with the type of the hydrogen bond. So let's begin the class now. So what is the meaning of the hydrogen bond here? Usually this hydrogen bond is formed by the four elements, hydrogen, along with more electronegative elements like fluorine, oxygen and nitrogen. So let us see the definition of the hydrogen bond here by taking an example of the water. So when we take the water molecule, there is a covalent bond between the oxygen and hydrogen. These are all covalent bonds, and hydrogen is a less electronegative element than the oxygen. And since oxygen electronegativity is more than hydrogen, it pulls these bonded electrons towards itself. As a result, most of the electron density try to concentrate closer to the oxygen, which gives a partial negative charge to the oxygen. Since hydrogen is losing the bonded electron density towards the oxygen, it attains the partial positive charge. Similarly, this side also, oxygen attains the partial negative charge, hydrogen attains the partial positive charges. So all these hydrogens attains the partial positive charges. So now this partially positive charged hydrogen and partially negative charged oxygen try to get attracted to each other because of the having the opposite charges. So this attraction force is a type of electrostatic force of attraction, but this electrostatic force of attraction is not arised from the pure charges. These partially positive charged and partially negative charges are not pure charges. Had they are the pure charges, this attraction force shall be strong like ionic bond. But these charges are not in that much magnitude like the pure charges. That's why the electrostatic force of attraction developed between these two atoms is weak. So that we can say that hydrogen bond is a weak electrostatic force of attraction between the partially positive charged hydrogen and partially negative charged any of these elements. Here we have taken example purpose oxygen. So partially negative charged more electronegative element like fluorine, oxygen and nitrogen is called as hydrogen bond. So that I'll write down the definition here. The weak electrostatic force of attraction between partially positive charged hydrogen and partially negative charged more electronegative element like fluorine, oxygen or nitrogen is called hydrogen bond. So it clearly says that the weak electrostatic force of attraction that exists between the partially positive charged hydrogen and partially negative charged more electronegative element. Then when different elements involved in the formation of the hydrogen bond and these elements are having the different electronegativities, then the strength of the hydrogen bond formed depends on the type of the elements involved in the hydrogen bond formation. So let us take an example here. We know that electronegativity order. Electronegativity of the fluorine is greater than the oxygen, which is greater than the nitrogen. So if fluorine is here, then it will get the more magnitude of the negative charge. If oxygen is here, it will get the magnitude of negative charge, whereas nitrogen, if it is present in this place of oxygen, it will get the lesser magnitude of the negative charge. So when the magnitude of the charges on the both of these atoms when increases, then the attraction force between the atoms also increases, so that the strength of the hydrogen bond gradually increases. So basically we can say that strength of hydrogen bond is directly proportional to the magnitude of charge. So higher the charge developed on these atoms, more shall be the strength of the hydrogen bond. And this magnitude of the charge depends on the electronegativity of atom. If electronegativity of the atom increases, magnitude of the charge increases, so that polarization of the bond increases, so that strength of the hydrogen bond also increases. So now let us take here, when fluorine develops the hydrogen bond with hydrogen, and oxygen develops hydrogen bond with the hydrogen, as well as nitrogen when develop the hydrogen bond with the hydrogen. See here the magnitude of the charge. Let us take delta 1 in case of the fluorine. This is delta plus. This is delta 2 negative charge, delta 2 positive charge, delta 3 negative charge, delta 3 positive charge. Apart from the hydrogen, if you take the fluorine, oxygen and nitrogen, obviously the quantity of the negative charge developed on the fluorine is more than the oxygen, which is more than the nitrogen. So that we can write down that delta 1 negative charge is more than the delta 2 negative charge, which is more than the delta 3 negative charge. So when the magnitude of charge increase, automatically strength of this hydrogen bond increase. That's why strength of the hydrogen bond formed by the fluorine hydrogen is stronger than the oxygen hydrogen, which is stronger than the nitrogen hydrogen bond. Now let us try to see how many types of hydrogen bonds are there. Hydrogen bond is basically of the two categories. They are, first one, intramolecular hydrogen bond, and second one, intermolecular hydrogen bond. So let us discuss the first one, intramolecular hydrogen bond. Intra in the sense within the molecule. That means both atoms, the atoms that are participating in the hydrogen bond, both belongs to the same molecule. So hydrogen bond is formed within the molecule. The atoms belong to the same molecule. So such type of the bond is called the intramolecular hydrogen bond. Let us take examples. Orthonitrophenol. Here hydrogen carries partial positive charge, oxygen partial negative charge. Between nitrogen and oxygen is more electronegative, gets partial negative charge and partial positive charge with nitrogen. So that here electrostatic force of attraction starts developing. Now here these both hydrogen and oxygen belongs to the same molecule. That's why we said that within the molecule hydrogen bond is formed. Such bond is called the intramolecular hydrogen bond. Now let us take one more example of catechol or benzene 1,2 diol. Partial negative charge and here partial positive charge, they also develop the intramolecular hydrogen bond. So we can write down benzene 1,2 diol. The next example is We can take salicylaldehyde. Where oxygen gets partial negative charge, hydrogen with a partial positive charge get attracted to each other. And one more example, salicylic acid, carboxylic acid, partial negative charge with oxygen and a partial positive charge with hydrogen. So here also both of these atoms belongs to the same molecule. That's why it is called the intramolecular hydrogen bond. Now let us see the other side, that is intermolecular hydrogen bond. Inter means between. So that we can imagine that between the molecules. So that the hydrogen bond is formed between the atoms of the two molecules. So that both of these atoms belongs to the two molecules. Let us take an example. The first one is, we can take the water molecule, in which let us take few water molecules here. Now all these oxygens attains partial negative charges, whereas hydrogens attains the partial positive charges. Now this partially negative charged oxygen starts developing the hydrogen bond with hydrogens which are closer to each. So we can imagine that one water molecule is developing the altogether 4 number of hydrogen bonds. In that 2 hydrogen bonds are coming from the oxygen and remaining 2 hydrogen bonds are coming from the hydrogen atoms. So total number of hydrogen bonds in the water molecule is equals to 4. And when water solidifies, it will go for extensive hydrogen bonding, so that all of these molecules undergo hydrogen bonding formation. And if you observe, there is a lot of empty space left behind among these water molecules when it solidifies. That leaves a lot of gap, and this gap decreases the density and increases the volume. So that is the reason why ice occupies, volume of ice is greater than the volume of water for the same mass. At the same time, density of the ice is less than the density of the water. That is the reason why ice floats over the water, because ice is lighter than the water. And one more thing is, whenever you are heating this ice, that means melting of the ice, it slowly breaks all these hydrogen bonds. So when these hydrogen bonds are broken, the molecule starts coming closer to each other. As a result, slowly volume decreases. When volume decreases, automatically density increases. That means when ice starts melting, its density gradually increases up to 4 degrees centigrade. The reason is, after 4 degrees centigrade, once these water molecules come closer to each other, again if you increase the temperature beyond 4 degrees centigrade, water molecule, that means liquid, starts expanding, so that again volume starts increasing. So that water H2O has the highest density at the 4 degrees centigrade. Now let us take one more example, ammonia. So in ammonia molecule also, Nitrogen attains the partial negative charge, all hydrogens attains the partial positive charges. Again here hydrogen bond starts developing, and this will be connected to the next nitrogen, and this is this side and this is this side. So altogether ammonia also forms total number of 4 hydrogen bonds. And next one, let us take another example of the hydrofluoric acid. Hydrogen partial positive charge, fluorines partial negative charges. So they start developing the hydrogen bond like this. Connect to the next hydrogen the other side. This is connected to the next fluorine this side. So that HF molecule is able to form only 2 hydrogen bonds. More than 2 hydrogen bonds are not possible by the HF molecule. The reason is, if it tries to develop one more hydrogen bond with any other fluorine atom, hydrogen like this, in the liquid state or in the solid state, then here fluorine is a smaller atom, carries the 3 lone pair of electrons, and other fluorine atom also carries the 3 lone pair of electrons. So lone pair repulsions between the 2 fluorine atoms do not allow the formation of the one more hydrogen bond by the fluorine with one more hydrogen atom. That's why fluorine can develop only one hydrogen bond in the HF molecule, but HF molecule develop the 2 hydrogen bonds. So in this way, if you take H2O molecule, ammonia molecule or HF molecule, all these cases, the atoms that are participating in the hydrogen bond formation belong to the 2 molecules. They are not from the same molecule. Ammonia is the one molecule, but within ammonia molecule it is not formed. Hydrogen of one ammonia molecule, nitrogen from the another ammonia molecule, hydrogen bond is developed. That's why this type of hydrogen bonds are called the intermolecular hydrogen bonds, and these are called the intramolecular hydrogen bonds. Let us see few more examples of the intermolecular hydrogen bond. Other examples: para-nitrophenol. So in case of the para-nitrophenol, partial negative charge, partial positive charge, partial negative charge and positive charge. So hydrogen bond is developed between the 2 molecules. Similarly, we can take the para-hydroxybenzaldehyde. Hydrogen bond is developed. Again, we can take the para-hydroxycarboxbenzoic acid. And this will connect to the next side, hydrogen bonds, and this hydrogen will connect like this, and here also this oxygen will connect this side, and this hydrogen starts connecting the other side, so it will continue. So these are other examples of the intermolecular hydrogen bond. Now let us see the specialities of the HF molecule and acetic acid molecule. HF molecule. So hydrofluoric acid, as I said, it forms the hydrogen bond like this in a zigzag manner. one HF molecule, as I said, it forms only 2 hydrogen bonds. This HF molecule develops the hydrogen bond in both solid state, liquid state, and even in the vapor state. So in vapor state, this HF molecule exists in many polymeric forms like HF taken 6 or HF taken 5. That means 6 or 5 hydrofluoric acid molecules still exist and acting as a single molecule even in the vapor state. So here, whenever you try to dissolve this HF molecule in water, do not expect the reaction like this, because fluoride ion do not exist independently in the water and it forms hydrogen bond itself. So that if you take this hydrofluoric acid, the bond shall break like this. Here one covalent bond will be broken, here hydrogen bond will be broken whenever it reacts with the water molecule, so that you can get like this. One hydrogen will be transferred to the water molecule, giving the H3O plus HF2 minus. This is called the hydrogen difluoride ion. So that hydrogen difluoride ion is having the hydrogen bond. You can see that this is the covalent bond is broken. This fluoride ion is forming the hydrogen bond and this fluorine through the covalent bond. So hydrogen difluoride ion is having the both covalent bond and hydrogen bond. But even though the covalent bond is stronger than the hydrogen bond always. Since fluorine forms the hydrogen bond even in the vapor state, HF2 minus ion exists. That is the reason why we can write down the formula with the potassium as KHF2. KHF2 exists, but not KHCl2. It will not exist. KHBr2 does not exist. KHI2 also do not exist because they don't form the hydrogen bond. And if you take the special nature of the acetic acid, acetic acid is a molecule that also forms the hydrogen bond in vapor state. So in vapor state, it forms the hydrogen bond and almost exists as the dimer. Dimer in the sense, two acetic acid molecules, after the formation of the hydrogen bond, they try to act as a single molecule. So here hydrogen bond is developed and here hydrogen bond. So the molecule looks like a single molecule now. So this is called the dimer of the acetic acid. Di stands for the two, mer means molecules are the parts. So two molecules exist as a single molecule. And one more reason is acetic acid, when you take the acetic acid and in the presence of the non-polar solvents like benzene, CCl4, etc., it exists as the dimer. But acetic acid, when you try to keep in the polar protic solvents like water, it will not exist as a dimer, but it undergo dissociation. CH3COO minus plus H3O plus. So these are some special natures of the hydrofluoric acid and acetic acid molecules. Now let us see the consequences of the hydrogen bond. Consequences of hydrogen bond. First of all, solubility. So solubility of the molecules in water we are discussing. So whichever the molecule is able to form the hydrogen bond is able to dissolve in the water. But when two or more molecules are able to form the hydrogen bond, in such cases, the molecule that develops the number of hydrogen bonds is more soluble in the water. So here we can write down that solubility is directly proportional to the number of hydrogen bonds. If number of hydrogen bonds are same, then it is inversely proportional to the molecular weight. Let us take an example here. When you take C2H5OH, ethyl alcohol, and ethylene glycol, and glycerol, here glycerol is able to form the more number of hydrogen bonds because it carries more OH groups. Ethylene glycol is having only 2 OH groups, so that it forms the lesser number of hydrogen bonds than ethylene glycol. Ethyl alcohol is having just only 1 OH group, that's why it forms the even lesser number of the hydrogen bonds than ethyl alcohol. That means solubility is directly proportional to the number of hydrogen bonds, so that higher the number of hydrogen bonds are with the glycerol, that's why it is more soluble than ethylene glycol, than ethyl alcohol. Next one is, what happens if the number of hydrogen bonds are same? Let us take an example, CH3OH, C2H5OH, C3H7OH. Now these three molecules are having the same number of OH groups, so that they can develop the same number of the hydrogen bonds. In such cases, solubility is inversely proportional to the molecular mass. Lower the molecular mass and higher will be the solubility. So that methyl alcohol is more soluble than the ethyl alcohol, which is more soluble than the propyl alcohol. Next, let us take the primary amines, secondary amines, and tertiary amines. In case of the primary amines, if you see the structure, so this nitrogen is able to develop the hydrogen bonds with the 2 hydrogens along with the nitrogen. So all these 3 are participating in the hydrogen bonds, so that we can expect that 3 hydrogen bonds are present in this molecule. And if you take the secondary amine, it has only 1 hydrogen to develop the hydrogen bond and 1 nitrogen to develop the hydrogen bond, so that hydrogen bonds available from this molecule is only 2 with the water molecule. And in case of this one, tertiary amine, there is no hydrogens, so hydrogen bond must and should come from the only nitrogen, that is also to the lesser extent. So more the number of hydrogens are with primary amine, that's why primary amines are more soluble than the secondary amines are more soluble than the tertiary amines. And if you take ammonia in comparison to this, so ammonia already we have seen that it is able to form the 4 hydrogen bonds. That's why it is even more soluble than remaining all these, so that we here ammonia more soluble, primary, secondary and tertiary amines. This is the solubility order. Now let us try to see how this boiling point and melting point are influenced by the hydrogen bond. So now let us see here both either boiling point or melting point directly proportional to the number of hydrogen bonds and strength of hydrogen bond. So that boiling point, melting point is the cumulative effect of the both number of hydrogen bonds as well as the strength of the hydrogen bond. We know that hydrogen bond formed by fluorine is greater than the oxygen, which is greater than the nitrogen. That means expected melting point and boiling point. Let us take this one is a HF molecule, H2O molecule, NH3 molecule. So if you consider only strength of the hydrogen bond, then the boiling point and melting points must be higher for the hydrofluoric acid than H2O than ammonia. When you consider the number of hydrogen bonds, HF is forming only 2 hydrogen bonds, this is forming the 4 hydrogen bonds, and this is forming the 4 hydrogen bonds. In such cases, melting and boiling points order could be equals to the H2O equals to the ammonia greater than the HF molecule. That's the reason why boiling point and melting point is not the individual property of the number of hydrogen bonds and strength of the hydrogen bond. It is the cumulative property of the both strength and number of hydrogen bonds. So that is the reason why the melting point order. Melting point is highest for the H2O molecule. Then if you take HF molecule and NH3 molecule, ammonia can develop the stronger hydrogen bonds in the solid state than HF molecule. I said already, the reason is if HF try to develop the more number of hydrogen bonds in the solid state, its lone pair of electrons do not allow to develop the one more hydrogen bond with the other hydrogen atoms. So that makes the HF molecule to develop the weaker hydrogen bonds in solid state than ammonia. That's why ammonia has the higher melting point than HF molecule. When it comes to the boiling point, so boiling point again depends on the number of hydrogen bonds. So again H2O has the higher boiling point. Now between ammonia and HF molecule, which is having the higher boiling point, we should keep one point in mind that melting point is the property of the solid. Solid has to melt. Boiling point is the property of the liquid. So in liquid state, we have to convert them into the gaseous state. So when you take the ammonia and HF, we already converted them into the liquid state. In liquid state, the strength of the hydrogen bond of HF is stronger than the NH3. The reason is, in liquid state, nitrogen being a larger atom and a less electronegative element, so that it cannot develop the stronger hydrogen bonds like HF molecule. That's why strength of the hydrogen bond of HF molecule is more than the ammonia. That is the reason why the boiling point of the HF molecule is more than the ammonia molecule. Then the question arises, what is the reason for the H2O molecule to have the both higher melting and boiling point values? See, oxygen electronegativity is in between nitrogen and fluorine. Oxygen atomic size is also in between nitrogen and fluorine. That means oxygen has the more cumulative effect of the number of hydrogen bonds and strength of hydrogen bonds than the nitrogen and fluorine. That is the reason why H2O is having the highest melting point as well as the highest boiling point values. In addition to this, how the type of hydrogen bonds like intramolecular or intermolecular hydrogen bonds influences the boiling point values. So let us take an example that we know that orthonitrophenol, which forms the intramolecular hydrogen bond, paranitrophenol is like this. So in case of orthonitrophenol, if you try to send this orthonitrophenol into the vapor state, you not necessary to break any number of the bonds because it is not connected to the any other molecules through stronger hydrogen bonds. But in this case, paranitrophenol, if you want to send this molecule to the vapor state, you need to break here hydrogen bond and here hydrogen bond, which needs the more amount of the energy. That is the reason why the molecules which form the intermolecular hydrogen bond cannot easily go into the vapor state. That's why their vaporization process is slow, vapor pressure is also less, at the same time they carry the higher boiling point values. So that the molecules with intermolecular hydrogen bond have the higher boiling point values than the molecules with intramolecular hydrogen bond. Next, other examples are, if you take HF molecule and HCl molecule, The boiling point of the HF molecule is more than the HCl molecule because hydrogen bond. HF molecule forms the hydrogen bond. That is the reason why HF molecule exists in the liquid state, whereas HCl exists in the gaseous state. And if you take the H2O and H2S, H2 is a liquid, H2S is a gas, and boiling point of H2 is more than the H2S. Reason, again, H2O forms the hydrogen bond, H2S don't have any hydrogen bond. And NH3 is a liquid, PH3 is a gas. Again, the boiling point of ammonia is greater than the pH3. The reason is here hydrogen bond is present. So due to the presence of these hydrogen bonds in HF, H2O, ammonia, they exist in the liquids. That means hydrogen bond is influencing the physical state of the molecules as well. Now, let us see the viscosity. Viscosity, we can understand in a simple way, that means thicker the liquid, more the viscous liquid. We can say that. So that viscosity is directly proportional to the number of hydrogen bonds. When number of hydrogen bonds increase, molecules are strongly attracted, so the molecule becomes more viscous. So the liquid becomes more viscous. So best example, if you take the ethyl alcohol and ethylene glycol and glycerol, so the viscosity of the glycerol is more than the ethylene glycol, which is more than the ethyl alcohol. Now let us see the formation of hydrogen bond in organic molecules. By organic molecules. Usually in organic molecules, hydrogen is bonded to the carbon atom. So if hydrogen is bonded to the carbon atom, it will not develop sufficient polarization and sufficient magnitude of the charges on both hydrogen and carbon. If the magnitude of the negative charge and positive charge is not developed sufficiently, that will not lead to the formation of the hydrogen bond. Hydrogen bond is weaker than the ionic bond, but it is closer to the ionic bond. The reason is, in ionic bond pure charges are involved, but in hydrogen bond partial charges are involved. That means whichever the molecules are developing the charges that are closer to the charges developed in the inorganic molecules, so they are also able to form the hydrogen bond. So hydrogen bond is not the property of only inorganic molecules, but any organic molecule can develop the hydrogen bond if it is able to develop the sufficient quantity of the charges on both hydrogen as well as the other atom. Let us see the examples here. Pure CH4 molecule do not develop any hydrogen bond. The reason here is carbon electronegativity is 2.5, whereas hydrogen electronegativity is 2.1. So sufficient polarization is not developed. But this hydrogen forms hydrogen bond when the carbon is bonded to the groups like G. This group could be, if it is chlorines, more chlorine atoms are there, cyanide, CHO, C double bond O, etc. So if this carbon is connected to the groups like more withdrawing groups like or more stronger minus I groups like these groups, then sufficient polarization shall be developed between the carbon and hydrogen, so that that hydrogen also will form the hydrogen bond. Let us take an example one by one. If you see the chloral hydrate, CCl3CH, OH taken twice. We also know that whenever two OH groups are present on the same carbon atom in organic chemistry molecules, the molecule is unstable, always loses one of the water molecule and produce the either aldehydes or ketones depending on the other group. Sometimes it produces the carboxylic acid if three OH groups are present. But chloral hydrate is stable despite having the two OH groups on the same carbon atom due to the formation of the hydrogen bond. So this chlorine, partial negative charged chlorine, partial positive charged hydrogen develops the hydrogen bond. Since it develops the hydrogen bond, these H2O molecule, OH groups are not able to undergo elimination process. That's why it gives stability to the molecule. And the next example is chloroform and acetone. See, acetone usually don't develop hydrogen bond with another acetone molecule or the hydrogen from the pure CH groups. That means if you take only acetone molecules, acetone liquid, so one acetone do not develop the hydrogen bond with another acetone. The reason in this case is why chloroform is developing the hydrogen bond with acetone is here this hydrogen carbon bond is more polarized. Why? Because it is bonded to the strong electron withdrawing chlorine atoms. So that makes this carbon hydrogen bond is more polarized, so that carbon, since it is losing its electron into the 3 chlorine atoms, it feels almost a positive charge, so withdraw the electrons from the hydrogen. That means the electronegativity of the carbon in this case is more than the electronegativity of the carbon in this case. Here carbon electronegativity is simply 2.5. It is more than 2.5. The reason is it is losing electrons. So when it is losing electrons, its electron pulling capacity from the lower electronegative element increases. That's why its electronegativity also increases. So as a result, hydrogen gets partial negative charge, carbon gets partial positive charge. Hydrogen gets partial positive charge and carbon gets partial negative charge. Sufficient charge is developed here. And what about the case of the acetone molecule? In acetone molecule, oxygen gets partial negative charge, carbon gets partial positive charge. And this partial negative charge easily developed because here pi bond is present. Pi bond is a weak bond. That's why oxygen try to pull the pi electrons more towards its side. As a result, partial negative charge is developed. So now this partial positive charge, partial negative charge are the sufficient magnitude of the charges are developed so that they can form the hydrogen bond. That means acetone forms the hydrogen bond with the chloroform. But if you take acetone with another acetone molecule, here hydrogen bond is not possible. The reason is here carbon though connected the C double bond group, what I said here, but only one group is bonded. If 2 or 3 groups are present, then sufficient polarization occurs between the carbon and hydrogen. Then only this hydrogen can develop the hydrogen bond. Otherwise it will not develop hydrogen bond, so that it will develop only dipole-dipole interactions. What is dipole-dipole in this sense? Here are some charges will be developed. Hydrogen will get the partial positive charge, oxygen will get the partial negative charge. But this partial positive charge is not same in magnitude as in this case. That's why this much strong bond is not formed. That's why such type of the bond simply called as a dipole-dipole interaction. This is also a dipole-dipole interaction, but stronger dipole-dipole interaction. That's why based on the strength, this stronger dipole-dipole interaction is separately called as the hydrogen bond. Molecules like formaldehyde, acetaldehyde, acetone are completely soluble. In water due to the formation of hydrogen bond. So this is about the hydrogen bond. Dear students, I hope you understand my class, and if you really understand my class, do like my videos and share it with your friends and subscribe the channel. Thank you one and all. We shall meet in the next class.